So this last example is not a function, and that's because I can think of a number I can plug in for x, and I can get two possible values for y. You're probably thinking, well, what number can you plug in for x? Well, what if I plugged in the number, let's say, -8? Then when I evaluated this, I would get the square root of positive 8 plus 1 is 9 is 3, and then I have plus or minus out in front of that. So I can have -8 getting mapped to 3, but I could also have -8 getting mapped to -3. And so therefore, since we have an element in the domain that's getting mapped to two different elements of the range, it's not a function. When we're dealing with variables like this, the independent variable is the variable that represents the domain, and the dependent variable is the variable that represents the range. So in terms of, you could think of it in terms of your mappings. That's one set, here's the other set. Things that get mapped from here to here, it's the independent variable getting mapped to the dependent variable. So most times in algebra, usually the x represents the independent variable, your horizontal on your graph, and the y will represent the dependent variable. But that doesn't necessarily have to be the case, as we'll learn later on. So let's talk about finding domain and range. What's the domain for each of the following functions? So here's the first one. Now this is just written as f of x is equal to 1 over the square root of x plus 2. So now we have function notation. Instead of using y is equal to 1 over the square root of x plus 2, we're just saying basically that y is a function of x. So what values can I plug in for x? Can I plug in any value, any real number? Well, I don't think so. I could plug in 1, I could plug in 2, I could plug in 0, that would work. I could plug in decimals, 5.7, fractions, 7/3. Those all seem to work. What about -2? Could I plug in -2? Well, that would give me the square root of 0, which is okay. The square root of 0 is equal to 0, but now I have a fraction 1 divided by 0, and that's not okay. So I know that I cannot divide by 0 here. I also know that I cannot take the square root of a negative number. So I have two things to consider here when I'm trying to think of what is my domain. So I know that x has to be greater than -2. If it's equal to -2, I get a divide by 0. And if it's smaller than -2, like -3 for example, then I would have 1 over the square root of -1. And square root of -1 is undefined in the real number system. So one way you can write the domain is an inequality like that, or we could use interval notation. And so for interval notation, we're going to write -2, comma, and then we'll go all the way up to infinity, and we're going to use parentheses around both of these. If we want to include the endpoint, we're going to use a bracket, a square bracket. But we don't want to include -2, so we're going to use parentheses. So that means it cannot be -2, but anything bigger. So for example, -1.9999. That would be fine, because when I plug that in here, I'm still going to get the square root of a very small positive number, which is fine. So you can represent your domain with an inequality or with interval notation here. And I'll start using more interval notation as we move forward in the course. How about find the domain of this? Now this is a set of ordered pairs. Well, this is going to be pretty easy because the domain is the first element in each ordered pair. So I just want to list those 4 specific values. So I don't want to write an interval, because an interval contains an infinite number of values. So my domain is going to be the set of those 4 values. And I'm going to put them in ascending order. So I'll say -4, 0, 1, and 2. Now, it isn't wrong unless you're asked specifically to put it in ascending order. But so if you just list it as 1, 2, -4, 0, that's fine. But those 4 elements represent the domain of this function. Let's look at other representations. Here we have a graph. What's the domain of this graph? Now what you could do is you could think of what are all the ordered pairs involved with this graph, or we could use a vertical line which will tell me what values of x are in the domain. So think of this as a domain detector, and as I slide this across the screen from negative infinity to positive infinity, whenever it hits the graph it's going to beep. Beep, 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 and then it stops, and then beep, 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 and then it stops, and it beeps one more quick time, and then it doesn't beep anymore. So whenever it beeps, the value of x is in the domain. And so it's going to start beeping right after this value, which is -4, and it's going to keep beeping until we get to -1. And then it's not going to beep at x equals 0, but right after that, any value greater than 0, it'll keep beeping until we get to 3, and then it won't beep until we get to 4, and that one time it'll beep, and then it won't beep anymore. I know it seems silly, but that's a nice way to remember how we figure out the domain. So when I write my answer here for the domain, and sometimes you'll see a D written like that to represent this is the domain. So we have -4 to -1. We're not going to include the -4. That has an open circle there. But we are going to include the -1, so we're going to have a bracket. And then union with, then we go from 0 to 3. And once again, we don't include 0 because that has an open circle. We are going to include the 3, union with. And then one other value, the value x equals 4. So that's not an interval, so I'm actually going to use set notation, and it contains the individual value of 4. And so that's how you could represent your domain. You could use inequalities, but that's going to be a little more tedious. So I'd prefer to use interval notation on that. Let's look at one more example. Find the domain of the area of a circle represented by this formula. And you're familiar with this probably. A is equal to pi times the radius squared. Now, if we're not thinking about a circle, an area, and we just look at this equation, you think I could plug in any value for r and I'm going to get any non-negative value for a. So no matter what you plug in for r, if you put a negative number, you're going to square it, which will make it positive, and then times pi, which will give you a positive answer. If you plug in 0 for r, you'll get 0, and so a is equal to 0. But you're never going to be able to plug in a value for r that'll give you a negative amount. But we know that for a circle, the radius has to be greater than 0. So our domain is going to be 0 to infinity. We never include infinity. It's not a specific number. And in this case, we're not going to include 0, because if the radius is 0, we don't have a circle. And so this is going to be your domain. And then the area can be any positive number as well. So that's different ways we can figure out the domain. What if I want to go back now and find the range of each of these functions? So that means what are the y values? What are the outputs going to be? So if we go back to the beginning, do this in a different color. So first let me write, this is your domain. So now let's do range. Well, f of x is equal to 1 over the square root of x plus 2. So for the range, you could maybe graph this and look at the graph. That would make it easier to see. Or we could think, well, what numbers can we plug in? If I plug in a number really close to -2, like -1.9999, when I add 2 to that, I'm going to get a really small positive number, 0.0001. And what happens when I do 1 divided by a really small number? Well, that's saying 1 divided by tens, hundreds, thousands, 10,000, 1 over 10,000. That's the same as multiplying by the reciprocal of the fraction. And that's going to give me a really big number. So it seems like the closer I pick a number to -2, but slightly bigger, the larger this entire expression is going to be. So, looks like I can go really high in terms of my range. So I can go to positive infinity. Well, what's the smallest value I could get out of this? Well, what happens if, let me draw an arrow here. So what I'm doing is I'm thinking of what happens to this expression when I plug in all the values in the domain. So when I plug in a number close to -2, I'm winding up getting a really big value for this expression. What happens if I plug in a really big number, like let's say 1,000,000? 1 divided by the square root of 1,000,002. Well, that's going to be a very large number in the denominator, and 1 divided by that will give me a really small number. So it turns out I'll be getting closer and closer and closer to 0. The bigger number I plug in for x, the smaller this fraction, and the closer it gets to 0. But I'll never quite get to 0, so I won't include that. And so that's my range, anything from 0 to infinity. We could check this by graphing 1 over the square root of x plus 2. Let's graph that very quickly. 1 divided by the square root of x plus 2. And you'll notice that as x gets really big, my graph is getting closer and closer to the x-axis, or the y value is getting closer and closer to 0. As my x values are getting closer to -2, my y values are shooting up. Now there's limitations on how high this graph will go on the picture, but we know from analyzing it that that just keeps going up and up and up and up. And there's actually a vertical asymptote at x equal -2. But that's more for later. All right, let's look at the domain for the second example. I'm sorry, the range. So the domain was here. Now we'll do the range. Well, that's going to be a set of all the outputs. So we had 7, we had -3, we had 1, and 7 showed up again. We don't need to write it more than once. And I'm going to put these in ascending order like I did for my domain. So -3, 1, and 7 would be my range. Those 3 specific values, as opposed to an interval of values. For number 3, if I want to find the range for this one, use the same idea as we did for domain, except we'll switch, and now we'll use a horizontal range detector, starting at infinity and going to positive infinity. And whenever it hits the graph, whatever the y value is there will be in my range. So at y equal -4, and then there y equal 1, and then y equal 2 all the way up to y equal 3. So let's list these. So for my range, I have a specific value of -4, and I also have, let me show you on this, so that's here. I also have a y value of 1 for many points on this graph, and so I want to include that, so positive 1. And then union with, and then from y equal 2 to y equal 4, except I'll never get y equal 4 because of that open circle, but everything between 2 and 4, not including 4, but including 2. So that's an interval of values. So we're going from 2 to 4, not including the 4, but including the 2. And that's your range. And finally, the area, we already talked about this. The domain was 0 to infinity, and same thing for the range. We can't get 0 area, but we'll get any positive value for the area as well. And so that's our range. I should stay color coordinated, make that green. And there we go. All right, let's look at one more idea. Another way we can represent an equation that is a function is use the notation f of x. I introduced that in the first example on the last page, instead of using y. So if I say that f of x is equal to 2x plus 7, that's the same thing as y equal 2x plus 7. And if I asked you to graph it, you would just graph the line with a slope of 2 and a y-intercept of negative or positive 7. So the value of f at x, or f of x, and a lot of times you'll see this used more when people are describing this notation than saying the value of f at x. But I like this because it explains what this notation means instead of just saying f of x. It's the value of our function at a particular x value. And the rule here is telling me that x gets multiplied by 2 and then we add 7. So when I think of a function here, the function says take whatever input you give it, that's the domain, it will multiply it by 2 and add 7, and that will be your output or your range. So let's look at this example. F of x is equal to x squared minus 7. I'm sorry, x squared minus 1. Let's evaluate. What's f of negative 3? Okay, well, let's start with that. This function says whatever you input, whatever x is inputted, it's going to take that and square it and then subtract 1. So if I'm inputting a negative 3, it's going to square a negative 3 and then subtract 1. So we simply need to do that. So we're going to do negative 3 and square it and subtract 1. And that'll give me 8. Remember, a negative times a negative is a positive. How about the next one? F of x plus 1. Now remember, this says the function takes whatever you inputted and squares that input. So if my input is x plus 1, I'm going to square the x plus 1 and then subtract 1. So I'm going to take the input, which in this case happens to be x plus 1. I'm going to square it and then subtract 1. Now what's x plus 1 squared? Remember, that means x plus 1 times itself. So you have to distribute there, and you're going to get x squared plus 2x plus 1, but then we're subtracting 1, so the 1's are going to cancel, and you'll be left with x squared plus 2x. Some people might want to factor out an x, not really necessary, unless you have specific directions for that. How about f of a? Once again, what does f do? It takes the input, squares it, and subtracts 1. So I'm just going to take a, I'm going to square it. I like to put parentheses for what I'm plugging in, even though I know it's not necessary. So I just had a squared minus 1. And that's it. There's nothing else I can do with that. Could factor it again, but not necessary. Lastly, this is the one that sometimes throws students. My function is defined as the input x is squared and we subtract 1. Here, my input is x plus h. So I'm going to square that and subtract 1. So I'm going to take x plus h, square it, and then subtract 1. Now, what's x plus h times x plus h? You have to distribute, or the code word for that is FOIL, multiplying the first, the outer, the inner, and the last. And when you do that, you should get x squared plus 2 times x times h plus h squared minus 1. There's no like terms there. We can't simplify it. So that's it. All right, so evaluating functions. You have to think of your functions as a rule. It's defining a rule for you. Inputs and outputs. So what if I ask you to evaluate this expression for that function we were just looking at? Now let me write that down. That function was f of x equals x squared minus 1. So let's start one piece at a time. First of all, what is f of x plus h? That means we take the x plus h, square it, and subtract 1. That's that part. I'm going to put brackets around there. So we realize that that was the f of x plus h. Let's change colors. Then we need to subtract f of x. What is f of x? Well, that was defined as x squared minus 1. Put brackets around that. we're subtracting these two things. And then in the denominator, we have h. So now I just have to simplify. But the first step, this is the first step, and that a lot of times is where students run into problems. Okay? Not understanding what f of x plus h represents in terms of whatever function we're given. So the rule for this function is square the input, subtract 1. So I'm squaring the input, which happens to be x plus h. I'm squaring that and then subtracting 1. So we've already done that. So let's write down what we have here. So we're going to have x squared plus 2xh plus h squared minus 1. And now careful here, we have to distribute this negative inside the green. So we're going to get minus x squared and then plus 1. And all of that is over h. So we notice that this minus x squared cancels with that positive x squared, and the 1's also cancel, that's 0. So I'm left with 2 times x times h plus h squared over h. But I can still simplify that. If you notice on the top, those terms I could factor in h out of. So if I factor in h out of 2xh, I'm left with x, 2x. And if I factor an h from h squared, I'm left with an h. If you're not sure, distribute that h and make sure you wind up with what we started with. Okay, and then we're dividing by h. And now because those are factors, I can cancel that because h divided by h is 1. And so my final answer is just 2x plus h. And later on when we start talking about limits and calculus, this difference quotient will become very, very important.